So let's go look at your lab. What do you think your lab is on?
Binary sort.
Man, y'all are just killing me here. All right. So this lab, we're going to practice in constructing a basic binary heap and performing heap sorts. Implement insert, copy constructor, get height, get size, contains first, remove first, aka remove the first element. Operator, subscript, remember this is an array, so I need to be able to at least look at what you have in there. And sort. Please follow the lecture, and some of this code will be done in class because we were going to start this lab in class.
Turn up.
What? Oh, time. Sorry.
Nothing.
All right.
Turn up. Turn up the class. Yeah.
Oh, did I say that?
No, I said.
Oh, okay, that's all right. Hey, look, sometimes I know some interesting sentences getting here. All right, first off, create an empty heap. Second off, does a deep copy of the array into a heap. Notice that you're passing it an array, and it's going to create a separate array representing a separate array internally that's a heap of the array you passed in. Okay? Given a value, add it to the heap. You must maintain the ordering, get the height, get the size. Contains. So we'll have to think about that.
Okay, hold on a second.
Yes.
So deep copy, we're going to copy the contents of an array into another array and then heapify that array.
Or just heapify your array as you're copying them in. We're not going to do deep copy in class, but hopefully once we've done a couple of these functions, you'll see that deep copy is really, really easy.
So you said.
Look, you can make this hard if you want to. I'm not going to stop you.
No.
I love to make it more difficult.
You'd love to make it more difficult?
I do not.
This is already too complicated as it is?
I don't try to, it just happens.
It's just, all right. So you ask if a value is inside the heap.
Just trying to pass the class.
Let's go look at the heap real quick. Whoa, just trying to pass this class. I just want to pass.
Just trying to get that C and move on, man.
Oh my goodness. Jonah. Now, if we're trying to find out if 9 is inside of this heap, how do we go about doing that?
You're gonna have to look through every node.
Yeah, you're gonna have to look through every node. There's no
easy way.
it's not like a binary search tree where you can search for it in login time. You have to go through every node. So contains is an O of N operation. Don't try and be tricky here. Just make your for loop and get it done. Operator subscript, that's just like for an array. We're actually going to do that in class. Remove first, I'm going to leave that one up to y'all. And the last one, perform a heap sort, return an array of sorted elements. Note the heap is empty after the sort. I'm going to try and at least get that started for y'all. And then, of course, don't forget to do your destructor. All right, do a week from today. Make sure there's no memory leaks. Add it to GitHub. All right, any questions before we start this lab a little? No? All right.
Not yet.
Not yet. But there will be plenty?
Yes.
All right. Oh, I am out of workspaces here. Wow, okay, we'll go over here. Lab 16, yeah. Okay. All right, let's fill out the private member variables of a heap. So if you're going to represent a heap that's templated on some class T, what do we need?
An array.
We need an array. Yeah, yeah, that. Now we'll call it the heap. All right.
Need some pointers.
We need some pointers. What would we be pointing to?
The children.
We need a root to show. No, wait, we need a node.
We don't need a node. No, we have an array. That's the whole point of a heap, is that you don't have nodes. You just have an array of all the elements.
Oh, well, man, then we don't need pointers.
Yeah, we don't. Well, we need a pointer to point to the array, but yeah, that's about it.
We need
Size. Okay, we're almost there. It'll be a little hard to see. All right, size. The size of, what's that the size of?
The array.
The size of, okay, the size of the array. So is that how many elements are in the array, or is that how long the array is?
That's how long the array is.
So, okay, that's just, all right. So
That's
what,
how many elements are in the array,
that's how many we can decide.
because that's what we use as the,
Okay.
we normally use as the size of the entire array, but now we need something that tells us how far to go each time we're going to decrement.
So usually with size, that is, that's how big the array is. So, or no, I'm sorry, that's how many elements are in the array. So another one we'll do in capacity. So capacity will say how many elements the array can hold, aka its capacity, and in size we'll say is how many elements are in the array. Would you prefer a different name for in size? Does that make sense what the difference is? Let me go and put up a comment so that makes some sense.
So we're going to be decrementing in size.
When you remove an element. Okay, that looks good. Let's, always a good first test. Did we break anything? Nope. Can we run it? Good. All right, we're doing great. Let's click on the CVP. All right. All right, passing in a constant int len. What does that sound like we're doing? Sounds like we're creating a new array of size len. M size will be, oops, 0. I just wrote that out there. And then capacity will be we're creating the array of size length. So how many elements can the array hold? Or the heap can hold?
The length.
Yeah. So the capacity is the length. All right, I'm going to do what's more commonly good coding practice, and once I store the capacity, I'm going to use that instead of the passed-in variable. Just programming practice. All right. Any questions about this one? All right. We need to insert an element. Oh boy. Well, before we insert the element, let's do this operator subscript. Since we're just using an array, this actually makes it pretty easy. We'll just return at the element at that position. That'll give us a way to test it. All right, insert.
If it's the first thing you're inserting, don't you just set it to root or set it to the beginning?
Okay.
You can always put it at M size, as long as M size is less than equal to capacity.
All right, there we go. Let's see. I'm going to let y'all do that. If M size is greater than or equal to capacity, then you're going to need to increase capacity before you can add it. All right. You got that, Matt? Okay, good. Otherwise, we now have enough room, so we'll just add it to M size equals the element. That puts it at the end. Don't forget to increase M size. And now what do we need to do?
Sift down.
Sift
Up.
up.
Those are the two options.
Yep.
Like this.
Check if we have capacity to add the element to the end to preserve left justification and balance. All right, 4 or 3 sift up to fix the heap property. To fix the heap. Maintain the heap property. All right. So how do we do that? Well, if I'm at I, where's my parent?
I minus 1 divided by 2.
Yeah.
Or I minus 2 divided by 1.
Let's go look at that. Let's go take a moment. If I'm at 11, which is 12, wow, that's hard to see. You said so 12 minus 1, which would be 11, divided by 2, which would be 5, which is the 14. Great. If I'm at 9, you're saying 11 minus 1, which is 10, divided by 2, index 5, which is the 14. So yeah, that's actually what's going on. You want to subtract 1 first, and then divide by 2. Okay? So, whoops, let's go to this side. Int parent index equals, we don't want m size plus plus, we actually want m size minus 2. It's minus 1 regularly, but we already incremented it, so it's minus 2 right now because we don't want to go too far. And then we want to divide that by 2. So that's the parent index. All right, then what do we do?
Check if it's greater than.
Okay. If m heap sub parent index is greater than
Greater than what?
The last element.
last element. All right, yeah. Well, that's good. And how did we get the last element?
ME times size.
Size minus 1, because we already incremented. I'm going to skip ahead. I'm going to make our current index m size minus 1, and then we'll go over here and we'll do current index, and this will all make sense in a moment, minus 1. Notice this is still all the same. I'm just putting in variable names so it makes a little more sense about what I'm doing. So if the parent index is greater than my current index, what do I need to do?
Swap.
Swap. No.
See the 10th variable?
Yeah. M heap sub parent index. Parent index equals to n.
Wait, so you're saying if the parent is greater than the child, swap?
Right. Good catch. Is that actually what we want?
No.
No. We want the other way around. All right. So if the parent is smaller than the current, we swap. All right. Are we done?
You need to do that multiple times.
You have to do it, yeah.
Which means we need a
Wow.
while loop. All right.
Wow.
While. All right. Well, this is still only going to run once because so after we swap, what do we need to do after we swap?
You need to update the current index and the parent index.
There we go. Yep. Current index is going to be parent index. And then do we need to change the formula for the parent index? No.
No.
We just copy paste. Copy paste. Copy paste.
Copy paste.
Copy paste. All right. Are we done now?
Should
Let's
there-
test it and find out.
Should there also?
That was the best answer yet. Thank you, Jonah. +5.
Yeah, that's a
You get plus 5.
pass. You gotta pass the class.
LMAO.
Insert test.cvp. So we're going to copy the empty test over to the insert test, just to create an insert test. So we need to first make a heap. So we'll do heap. Heap. Oh, let's make a pointer. Heap equals new heap. We'll make it 100 elements. And these are templated, so I almost forgot to do this. There we go. And let's make sure we delete the heap afterwards. All right, so let's do heap.insert. What do we need? Give me some values.
18.
4.
18 and 4. Let's test that first. And then we want to make sure that, well, if we insert 18, assert equals, then heap sub 0 should be equal to 18. Or actually, I'm doing this backwards. 18 should be the value in heap sub 0. And in heap sub 1, the value should be 4. Does everyone see that? Okay. Let's make the insert test and see how many errors come up. Oh, only a couple. Ah, little arrow, eh? Oops, because it's on the heap is being created on the heap. So we need to have the arrows to actually dereference the pointer. Something failed. Oh no.
Does anybody else hear this like buzzing noise?
Yes.
I don't know what it is.
Like a faint buzzing.
Yeah. On the ceiling.
All right, we're going to go ahead and assert this. Let's see if that fixes this issue. Nope. Error no match for operator are int and heap sub int. That doesn't make any sense. Oh, curses. I forgot to dereference it first. Oh, that's annoying. All right. Okay, that worked. Let me put the equals back. So the issue here, because C++ is like this, is that you had to dereference the heap before you get the subscript. Because C++ is like this. Yep. All right. Yeah, well, that's good. We passed our first test. Let's go make another test. If we add them in the reverse order, should 18 still be up top?
Yes.
Yes. All right, let's do that. Didn't like that, probably because we need to have something called test2 instead. Oh, man, we're doing great. All right. Give me another value after 8. Another value. 22. So if we had 22 in this order, what should be the first number?
22.
22. Then what should be the next number? Ooh, let's think about this. It could be either one, and this is where trying to test the heap starts to get a little tricky. But we're adding, what was it? 4, 18, and 22, right? So we start with 4, and we're good, right?
Yes.
So we're next going to add 18. Do we need to do anything?
You set it up.
Sniffed up. 18 and 4. All right, then comes the 22. We need to sift up. So we add the elements in that order. The heap should be this. All right. A little tricky on how to test this, but that's how it's got to be. So the second element should be a 4, and then the next one should be an 18 at the end.
Oh,
Thank you. Do you see how creating these different test cases make it easy? Because I'm just copying and pasting, and that way if you ever, the point of this is if you go off and do something else, you can just rerun the whole test and you're done. If you end up having to change things around. All right, let's let's start adding a bunch of elements. This time I'm first going to change this to test 4 so I won't mess up that again. All right, so let's add a whole bunch of them. Oops. All right, go ahead and give me some values.
74.
74. 9,000.
Oh, wait.
You want 9,001, don't you?
Yeah.
Okay. 2.
2.
-5.
-5.
6.
6. All right. Let me write these on the board so we can figure out if we're doing this right. After the 22 comes 74, 9,001, 2, -5, and 6. Okay, perfect. So I wrote those up on the board. Ooh, nice, beautiful glare. All right. 74. Where does 74 go?
What?
Right here. 74. Right. Do we need to do anything? Sift up. So we take 74. 74, 4. Do we need to sift up again?
Yeah.
I'm just trying to make sure that's perfectly clear what's happening. So on exam, you'll get this right. All right. Are we done? Now, where's the 9,001 go? To the right of the 4. Perfect. All right. Do we need to do anything? Sift up. Do we? Oh, need to do anything? Sift up again. Okay. Are we done? And was 2 really next, or was it 12? It was 2? Okay, great. Where's the 2 go? Yeah. Are we done?
Yes.
All right. Where's -5 go? All right. Are we done?
Yes.
Beautiful. Good job choosing those numbers. All right, 6. Where's 6 go? Left of the 4, right over that glare. All right. How's that look? Oh, that's not too bad. Sorry, guys at home, that's a 6. Actually, I'm going to do this. All right. But it's about to be a 4. Because we do have to sift it up. Are we done?
Yep.
Yeah.
All right. So, what should be the array?
9,001.
9,001.
74.
74. You're good. 18.
6.
6.
22.
22. 2.
-5.
Man, these are the worst boxes I've ever drawn in my life. And
It slowly got smaller as you went on.
Dr. West, you said you're really good at drawing boxes.
Yeah.
I never said anything
No,
about.
you did. You told me
I never said anything about perfect boxes.
You said
You know,
when I went into your office, you
I just said I'm good at drawing boxes. I can draw all kinds of boxes.
so I can make perfect boxes.
I
I'd
can.
love to see a perfect box.
Wow, that was rough.
I'm disappointed. You empty promises.
Show me a big box.
Wow. Tough crowd. All right.
You can't ever.
Seven. How many elements are in here? Or are there 8? There's 8 elements. All right. So after the 18 comes the 6, 22, 2, -5. Oh, that would have been bad. And a 4. Wait, is that really all of them? 18, 6, 22. Okay, great. All right. Huh.
Nice.
You know, whenever things work out this well, I like to say, wait a minute, am I actually running correctly the first time? Okay, I am. Because notice I put in a test case that was wrong just to make sure it's testing correctly. Always a good thing to do real quick, because usually everything working the first time, it means something is not working correctly.
Preach.
Just being honest. Okay. Yeah, so I think our insert's actually working very well. Let's go ahead. All right, we did insert. Man, it's beautiful. Operator, heap sort. All right, I'm going to give you. Let's see. Ooh, how to explain this one? So heap sort. Remember, at this point, let me make this comment. At this point, the array has been heapified. So this is a little different than the slides, because by adding it to the heap object, the array has already been heapified, because by adding it with insert or with your deep copy, it's already a heap. Okay? So it's already been heapified. That part's already been completed. So what you want to do essentially call remove first and make that element the last. Well, hold on. Keep calling remove first. Hold on a second. Let me rephrase this. Yeah, you want to swap the last. I'm trying to make this easy for you. We want to swap the last, first and last element, then reheap, and do that until m size equals 0. Okay. Now for some reason I didn't copy over remove first. We're not going to do that one in class, but I'm going to try and help you here by making this one a lot easier. Remove first. Step 1. You don't have to do it this way, but if you do, the heap sort is going to be super easy. Swap the first and last element. 2. Decrement m size. 3. Reheap. All right. So if reheap, and then 4 return m heap sub m size, which is going to be the actual last element. That's technically not part of your heap, but you moved it over there at this one point in time, so this is legit. This is okay to do. Why am I recommending to do it this way?
Because you know best.
Because I know best. Good. Why is this helpful to do it this way? If remove, yes?
If you figure out the remove first, then all you have to do for heap sort, like after you did that, all you have to do for heap sort is, while m size was not equal to 0, just keep recalling remove first, right?
Mm-hmm.
Magic.
Wow, that made it real easy now.
Yeah.
All right, this is almost correct. It's almost correct. Your professor's going to be very, very evil.
So
And
we're gonna have to check to make sure it's not null.
what should M heap be after you return from heap sort?
Sort.
No. Your heap must be empty. Right, because you're going to return the array sorted, so I'm going to use the data you just returned to do something with it. So you don't want me manipulating your internal data, so you need to create a temporary variable here. And what does n capacity need to be at this point? 0. All right. Now I've been really nasty. Okay. Any questions? All right. I think y'all can take it from here. Let me make sure this code compiles. Nope. T does not name a type, probably because we need to put the whole template thing in front of it. Perfect,
I've
beautiful.
had that error before, and I was so upset because I was like, "Why isn't it?" And then I realized I was like, "Oh."
And let me make sure I did all the naming is correct. Heap sort, great.
Happens with those brackets, a bit more forward.
Yeah, it doesn't. It's like.
I'm going to go ahead and
this
add
is-
everything to it. Git commit -m lab 16 class code.
Errors were-
Git push. Oops, I accidentally left the insert the swap file open. Sorry about that. Let me go ahead and go back here, git rm. What do we want? Test. And I accidentally added the swap file, so let me remove the swap file real quick. Swap file cleanup. And go ahead and push that. Okay. All right, so that's all your code. I think you have your lab and your project. Any other questions? You're going to have an hour and a half of lab time. All right. Okay.
What?
I have to do my schedule.
Are you serious?
Yeah.
If there are no more questions, real quick, just to make sure we recap, what is the difference between a heap and a binary search tree?
Heap is not cheap.
Heap,
It also uses an array instead of a.
you can represent a heap with an array.
Yeah.
The root must be greater than the children.
Then it's shown both children. But with the binary search tree, each node is
Less than. Less than and on the left side and greater
on the right foot
Yeah.
side. Now what the heap has a heapify property where it has to be greater than both of its children. Binary search tree has the property where each node, everything to the left has to be less than, everything to the right has to be greater than. Good. What two things must you have for it to be a heap in addition to the heap property? We totally do.
I mean, well, okay.
Not justified.
Left justified and
Balanced.
Balanced. Perfect. Binary search tree does not have to be left justified or balanced. But you'll find out in project 3 that having them balanced is very tricky. But they don't even worry about left justified because that's ridiculous. Anyways, for a binary search tree. Any other questions? Great. All right, guys. Today's Wednesday, right?
Yeah.
Well, have a good weekend. See you on Monday.
Good day. Yeah.